Okay, to start off, I'm Brent Wallace. I'm from Phoenix, Arizona.
I'm Alaska Gazal from North Michigan.
And I'm Megan Reeves from New York.
And our missing member is Serena Young. She's from California.
All right, so there's a bit of background that you need to understand before we get to the presentation. So one thing that happens is that there are photons all around us, and when a photon strikes an electron actually likes to jump into somewhat what we call an excited state. Basically, it's just a more energetic state. After a short amount of time, the electron then jumps down from these higher energy states and releasing a photon of equal energy that it took to rise up to that state. These photons have high amounts of energy and are known as X-rays. These are the photons generated by the electron jumping down. And this is just a diagram to show that when you do strike a photon into an electron, it does go into an excited state. So sometimes these photons are actually pretty powerful, and they're actually strong enough to eject electrons from an orbital shell. So electrons, just not to get too detailed, like to live in these orbital shells that live inside atoms. And so what happens is when there's a photon that's actually strong enough, it can knock these out. And what happens is the electrons that are in higher orbital shells will actually jump down to a lower orbital shell to fill the missing gap that the electron has just left. And that difference in energy will then release another photon, which both these processes of the electron jumping down, releasing a photon, and the one where the electron goes into a higher energy state and goes back down again, is known as, they both produce X-rays, and they're both called X-ray fluorescence anytime a photon leaves. Another thing that we're going to get to a little bit later in the presentation, there is this specific law called there's a thing called Moseley's law, which basically is a law that describes the relationship between the atomic number and the energy of a photon that's released from the atom. We're going to talk about that briefly later.
The objective of the experiment that we performed was to determine if two rings that were claimed to be made in 1st century England and 11th century Scandinavia were actually made in those two time periods. We tested the rings in the experimental setup shown in the images. The equipment shown consisted of an X-ray tube that emitted X-rays onto our targets. Our targets then emitted electrons that were detected by our silicon lithium detector. Our silicon lithium detector was powered by our energy supply, which was set to -500 volts. The electrons that were emitted after going through the detector were then converted by an analog to digital converter into a signal that the computer could then understand. And the computer then gave us readings based on the signal that it received on which traces of elements or metals were found in the rings.
This is the data that we collected for the wideband. As you can see, the majority of the X-ray counts fall under this 8.04 kiloelectron volt energy for copper. We thus deduce that the majority of this ring's elemental makeup is in fact copper. However, we also found traces of zinc right here. Zinc emits what are called K-alpha X-rays at energies of 8.6 kiloelectron volts. This peak right here signifies the presence of that element. And we also found iron. Over here on the left, it emits K-alpha X-rays at energies of 6.4 kiloelectron volts. Something important to note here is the correlation between atomic number and emitted X-ray energy. And this is important because, as Elias said earlier, Moseley's law says that there should in fact be a relationship between these two properties. So let's take a closer look at our data and see if we can depict a relationship between the two. We start out all the way on the left here with iron. Now iron has an atomic number of 26, it's denoted Z right under here. That basically means it has 26 protons or positively charged particles inside its nucleus. It emits radiation, or it emits X-rays at energies of 6.4 kiloelectron volts. As we go to the right on the graph toward higher energies, we then run into copper. Copper's atomic number is 29. Again, this is higher than iron's 26. And correspondingly, its emitted X-ray energy is higher as well at 8.04 kiloelectron volts. More energetic still are the X-rays emitted by zinc, zinc's atomic number being 30, which is again higher than copper's. So clearly, our data supports the fact that there is a positive correlation between atomic number and emitted X-ray energy. And this is the data we collected for the wideband. As you can see, again, the elemental makeup of this ring is dominated by copper. Its signature 8.04 kiloelectron volt X-ray energy. What really differentiates this ring from the other ring, however, is as you can see, we can't really collect any other data that shows us that there's strong elemental makeups from other elements in this ring. So this is a K beta X-ray from copper. It's basically telling us that we have the same element in here. However, our detectors are limited to energies of 60 kiloelectron volts, and elements are known to emit X-rays at energies higher than those, so we wouldn't be able to pick up those energies. But it is safe to say that the majority of this elemental makeup for this thin ring was copper as well. And lastly here, we have plotted accepted values, so like values off the periodic table, of K alpha X-ray energy as a function of atomic number. And this is Moseley's law defined quantitatively from accepted values that we know from the periodic table. Now, as you can see from this leading term here, it is a quadratic relationship. But most importantly to note is that we get the same positive correlation between atomic number and X-ray energy that we did in our data earlier. So thus our data corroborates the accepted relationship between atomic number and X-ray energy that is Moseley's law.
And then once we were finished doing the experiments and analyzing the data, as Brent was talking about, we wanted to answer the original question of whether the rings were real or fake. So we went back and researched some of the common metals that they had access to in England and Scandinavia in the centuries that the rings were supposed to be from. And the wide ring was supposed to be from England, and it contained, as Brent said, a lot of zinc, which was not a common element that was found in England or used in metalworking during that time period, so we can conclude that it's likely fake. And the same thing with the ring from the 11th century Vikings. It also had a lot of zinc, which they did not have much access to. So both of the rings are likely fake, but we can't be completely certain because of the error that's inherent with everything, with every experiment that you do. And the second part of the question was whether or not the rings were worth their weight in metal if they weren't fake, if they were fake, I mean. And copper and zinc both sell for just under a cent per gram, and the rings were both about 3 grams, so they don't come close to the asking prices of $30 and $35. And once we were finished, we finished early, so we decided to play around with some other things and see what sort of composition they had. So the first thing we tested was that rock in the picture, which had high contents of iron and sulfur, which make up fool's gold or pyrite. And we also did vitamin pills and the dorm keys that we had, and found the different elements that made them up.
Basically, we ran out of time and wanted to shoot X-rays and stuff.
We also used Elias and my glasses, the paperweight over there, which was also made of iron, and like one of the previous groups, we tested pennies from before and after 1982, which did have different amounts of copper and zinc in them. And that's the end of our presentation.
So these are bloopers from Serena's.
You're not actually going to show me messing up, right?
Yeah.
So the objective of our experiment was objective of our experiment was to determine